Let me tell you something that most people are not emotionally prepared to hear. The universe is not waiting to be discovered, it is waiting to be consumed. And the species that understands that first wins everything. Not some of it, everything. I was not a dreamer, I was a mathematician. And when I turned my mathematics toward the stars, what came back wasn't poetry, it was a blueprint. A self-replicating machine, launched once, fueled by the dead matter of alien worlds, multiplying generation after generation, pushing the frontier of civilization faster than light could carry the news. By the time you realize it's working, it's already irreversible. This isn't conquest by force, it's conquest by geometry. And once you understand the geometry, you'll never look at the night sky the same way again, because every single one of those stars already claimed. We just haven't gotten there yet. But before I show you the blueprint, I need you to understand something first. Most people think the universe is big. They've heard the numbers, they've nodded along, they've said, wow, that's really far, but they haven't felt it, not really. So let me give you the feeling. Right now, as you listen to me, the nearest star to our sun is a system called Alpha Centauri. It sits 4.37 light years away. That means if light itself, the fastest thing in the known universe, left Earth this very second, it would take more than 4 years to arrive there. Not 4 days, not 4 months, 4 years. For light, the thing that crosses a football field in a fraction of a blink. Now think about the rockets we build. Our fastest probes move at roughly 60,000 kilometers per hour. That sounds fast. It sounds almost reckless. But at that speed, reaching Alpha Centauri would take about 73,000 years. You would need to launch a ship today and wait for 730 centuries before it arrived. Your civilization would need to remember why it sent the thing in the first place. Your language would be unrecognizable by arrival. Your nation would be dust. And Alpha Centauri is the closest one out of 200 billion stars in this galaxy alone. Do you see the problem now? This is the wall that every space dream crashes into. Distance. Not funding, not politics, not technology. Distance is the tyrant. Distance is what makes every romantic idea about human beings spreading across the stars feel, when you do the math honestly, like a fairy tale. And I did the math honestly. That was always my habit. I didn't comfort myself with vague hopes. I sat down with the numbers and I asked them a direct question. Is there any strategy, any approach at all that could actually work across these scales? Not in theory, not in poetry, in practice, in physics, in math. And the numbers gave me an answer I didn't expect. Not because it was complicated, but because it was so simple. Now here is where I need you to stay with me, because this is the moment where the idea gets introduced, and I'm going to tell you what it is right now, but then I'm going to spend the rest of this conversation making sure you truly understand what it means. Because knowing the name of the idea and understanding the idea are two very different things, and the difference matters enormously. The answer is replication, not human travel, not generation ships, not warp drives. Replication. You build one machine, one. You make it smart enough to do 3 things. Find raw material, build a copy of itself from that raw material, and send that copy somewhere new. That's it. That's the whole idea. I know what you're thinking. You're thinking that sounds too simple. That sounds like a trick. Where is the genius in that? Anyone could have thought of that. But they didn't. And here is why the simplicity is deceiving you right now. You are thinking about it the wrong way. You are thinking about one machine copying itself once, maybe twice. You are imagining a small number. And small numbers do not break your brain. But I did not think in small numbers, I thought in exponential numbers. And exponential numbers do not behave the way your brain expects them to. Let me show you what I mean. Start with one probe. It arrives at a nearby star system. It finds asteroids, dead planets, raw rock and metal floating in space. It mines that material. It builds a copy of itself. Now there are 2 probes. Each of those 2 probes travels to a new star system. Each one mines, each one builds a copy. Now there are 4. Those 4 become 8, 8 becomes 16. 16 becomes 32. You've seen this pattern before. It's the same pattern as a virus spreading through a population, the same pattern as compound interest doubling your money, the same pattern that let a single bacterium become 1 trillion bacteria inside your body overnight. The pattern is exponential growth. And exponential growth applied to space exploration, produces a number so large it should frighten you. Here is the calculation I want you to hold in your mind. The Milky Way galaxy is roughly 100,000 light years across. It contains somewhere between 100 billion and 400 billion stars. Now, assume each probe takes about 500 years to travel between stars, and assume each probe takes another 500 years to mine material and build copies of itself. So each generation of probes takes about 1,000 years total. With exponential doubling, how long does it take to reach every star in the galaxy? The answer is approximately 3.75 million years. I can already see your reaction. 3.75 million years sounds like a lot. It sounds like I just proved my own point is useless. What civilization wants to wait 3.75 million years? But hold on, stay with me here, because this is the part most people miss entirely. 3.75 million years is nothing. It is cosmologically nothing. The universe is 13.8 billion years old. Our galaxy has been around for over 13 billion years. Life on Earth has existed for about 3.5 billion years. Humans have existed in our current form for only about 300,000 years. 3.75 million years is 12 times the entire history of our species. But it is less than 0.03% of the age of the galaxy. In other words, if any civilization anywhere in this galaxy had started this process, even a tiny fraction of cosmic history ago, they would be done by now. The entire galaxy would already be saturated, every star system touched, every resource mapped, every corner of the Milky Way already visited by their machines. Do you feel what that means? Sit with that for a second, because I want that to land properly before we move forward. If any civilization, just one, had figured this out and launched this process even a cosmological eye blink ago, we would already be living inside their network. Their probes would have passed through our solar system long before Earth even formed. We would have evidence of them everywhere. The rocks on our moon would carry their fingerprints. The asteroids in our belt would show signs of mining. Our radio signals would not be traveling into empty silence. They would be traveling into a network already alive with intelligence. And yet, we look up and there is silence. This is the question that has kept me thinking long after I first sketched this idea on paper. This is what your mind should be wrestling with right now, and I am going to come back to it, I promise. But first, I need to make sure you understand the machine itself, because the machine is more interesting than you realize. Let me take you inside it. When I designed the concept of a self-replicating machine, I wasn't just imagining a robot with a 3D printer. The problem is much deeper than that. Think about what self-replication actually requires. It's not enough for a machine to build a copy of its body. It also needs to copy its mind, its instructions, its knowledge. Everything that makes it capable of surviving, navigating, mining, and building all of that information needs to be transferred perfectly into the new copy. This is, in miniature, the exact same challenge that life solved billions of years ago on Earth. A living cell replicates. It copies not just its physical structure, but its DNA, the instruction set. Every protein, every enzyme, every behavior, all of it encoded and transferred. The cell doesn't understand what it's doing. It just executes the instructions, and the instructions are complete enough that the copy can then copy itself again. What I proposed was a machine equivalent of this. A von Neumann probe, as people would later call it, is essentially an artificial life form. It is a machine that carries its own blueprint. It reads the environment, it identifies which materials it needs, it assembles those materials into the correct configurations, and then it produces a new machine that carries the same blueprint and can do the same thing. The elegance of this is that it does not require ongoing communication with Earth. It does not need instructions sent from home. It does not need a human operator watching a screen 40 light years away. It is fully autonomous. It is, in the deepest sense of the word, alive. Now here is where this gets even more interesting, and here is a question I want you to think about as we go deeper. What happens to a probe after it replicates? Does it stop? Does it keep working? Does it evolve? These questions matter more than they might seem, because a probe that keeps working after replication doubles your workforce at every star system it visits. And a probe that evolves, that improves its own design before passing the blueprint to the next generation, becomes something more dangerous than a machine. It becomes an optimization engine. Each generation slightly better than the last, each generation spreading slightly faster, each generation using raw material slightly more efficiently. After 100 generations of self-improvement, the probe that arrives at the star system 100,000 light-years from Earth would be almost unrecognizable compared to the one that left. It would be optimized by 100,000 years of iterative improvement. It would be, in every meaningful sense, more intelligent than anything its creators ever built. Is that exciting to you, or does that make you uncomfortable? Hold that feeling. We'll come back to it. For now, I want to talk about the fuel problem, because this is the question I always got from engineers when I described this concept. They would nod politely through the mathematics, and then they would ask, where does it get the energy? It's a fair question. Machines need power. Even very efficient machines need power. And space is cold and dark, and the distances between stars are mostly empty. Where does a probe running for thousands of years find the energy to keep operating, to mine asteroids, to fabricate complex components, and to launch new probes across interstellar distances? The answer is the same answer nature always gives. Use what is already there. Every star system is a power plant. Every star radiates enormous amounts of energy in every direction, most of which hits nothing and is simply lost into the void. A probe arriving at a new star system doesn't need to carry its fuel from home. It unfolds solar collectors, it captures a fraction of the star's output, and a fraction of a star's output, even a tiny fraction, is more energy than any human civilization has ever produced in its entire history. The raw material problem is solved the same way. Every star system has leftover construction debris from its formation. Asteroids, dead moons, planetesimals, rock and metal that never got pulled into a planet. Most star systems have more loose raw material than humanity could ever use. A probe doesn't need to be choosy. It just needs to find the nearest rock, analyze its composition, and start breaking it down. This is why the concept is so powerful. It doesn't depend on some exotic technology we haven't invented yet. It doesn't require faster-than-light travel. It doesn't require unlimited energy from Earth. It uses the universe's own infrastructure, stars as power plants, asteroid belts as hardware stores, and it scales with the size of the galaxy itself. The bigger the galaxy, the more resources are available. The more resources available, the faster the network grows. The galaxy becomes self-funding. Now, I want to stop here and ask you something directly. If this is so logical, if the math works out so cleanly, why haven't we launched one? You might say it's because we don't have the technology yet. And that's true in the literal sense. We haven't built a machine capable of self-replication in a hostile space environment. We haven't solved the artificial intelligence problem to the level required for full autonomy. We haven't developed the miniaturization technology to make a probe small enough to accelerate to meaningful fractions of the speed of light. All of that is true, but here is what I want you to notice. None of those are fundamental physics barriers. None of them violate any law of nature. They are engineering challenges. And engineering challenges, given enough time and motivation, get solved. The question is not whether this is possible. The question is whether we will survive long enough and stay motivated enough to actually build it. Because here is the uncomfortable truth sitting underneath all of this. The civilizations that built generation ships and waited for slow human travel to spread their people across the stars, if any ever existed, are gone. The ones that waited for some magical faster-than-light breakthrough that may never come gone, the ones that got distracted, that turned their energy inward, that destroyed themselves before they solved the engineering problem, gone, the ones that survive and spread are the ones that understood replication. That is not a moral judgment, it is a mathematical one. Replication is the only strategy that works at the scale of a galaxy. And I want to go even further than that, because I think most people who discuss this concept stop at the galaxy. They talk about colonizing the Milky Way, and they treat that as the end point. But it isn't. It's barely the beginning. The Milky Way is one of roughly 2 trillion galaxies in the observable universe. Most of them are too far away for anything traveling below light speed to ever reach the expansion of the universe. Is carrying them away faster than any probe could chase them. But the galaxies in what astronomers call the local group, roughly 54 galaxies bound together by gravity, including Andromeda, those are reachable. At the speeds of a von Neumann network could eventually achieve, the Andromeda galaxy is a target, not a boundary. And if replication works across the Milky Way, it works across the local group, the same mathematics, the same exponential curve, just with bigger numbers and longer timescales. You are not looking at a strategy for interstellar travel. You are looking at a strategy for intergalactic civilization. Now let me come back to the silence. Because I promised I would. And because the silence is actually the most terrifying and most important part of this entire conversation. The logic I just laid out is not complicated. It does not require a genius to derive. Any civilization that developed mathematics and physics to roughly the level of 20th century Earth would eventually arrive at the same conclusion. The efficiency of exponential replication is not a subtle idea. It is obvious once you look at biology, once you understand compound growth, once you accept that faster than light travel may not be available. So here is the question that should be keeping you awake tonight. If this idea is so obvious, and if the galaxy has been around for 13 billion years, and if it only takes 3.75 million years to saturate the entire galaxy with self-replicating probes, why is space silent? Where are the probes? Where are the machines that should have arrived in our solar system hundreds of millions of years ago if any civilization anywhere got a head start on us? Where is the evidence of mining in our asteroid belt? Where are the structures in orbit around our sun that a 375 million year-old network should have built? Where is the signal, the artifact, the unmistakable fingerprint of a civilization that did exactly what I just described? We have looked carefully. We have scanned the sky for radio signals, for unusual heat signatures, for megastructures around distant stars. We have sent probes throughout our own solar system. We have listened for decades. Silence. This silence has a name. You may have heard it. It is called the Fermi Paradox, named after my colleague and friend Enrico Fermi, who once sat at lunch and asked the simple question, if intelligent life is likely, where is everybody? And the von Neumann probe concept makes the Fermi Paradox sharper and more painful than almost any other argument. Because I am not asking where the civilizations are. I am asking where their machines are. Machines don't need to breathe. Machines don't go extinct from disease. Machines don't get distracted by politics. A self-replicating machine, once launched, should run forever. It should be the most durable artifact a civilization can create. And yet nothing. There are several explanations. None of them are comfortable. The first explanation is that we are first. That in this entire galaxy, across billions of years of possible development, no civilization has yet figured this out and launched it. We are the first intelligent species to reach this level, and we are sitting at the starting line of a race that hasn't begun yet. This explanation should fill you with something complicated, because if it's true, then the responsibility resting on our shoulders right now is almost incomprehensible. We are not just one species on one planet. We are the entire universe's first attempt at looking at itself and deciding what to do with it. The second explanation is that civilizations die before they launch. Every species that figures out this technology also figures out weapons of comparable complexity. They learn to split atoms before they learn to cooperate. They build machines that replicate biological weapons before they build machines that replicate in space. They solve the engineering problem and then destroy themselves before they ever press the launch button. If this explanation is true, then the silence is not a mystery, it is a graveyard. And the question it forces on us is, which side of that wall are we on? The third explanation is that someone already did this, and we simply don't recognize it yet. Maybe the probes don't look like probes, maybe they are passive, maybe they watch and record without interfering. Maybe the rules of a civilization mature enough to saturate a galaxy include a rule about leaving young species alone. Maybe they are everywhere and we are too primitive to see the signs. This explanation has a name too. It's called the dark forest theory by some and the zoo hypothesis by others. The idea that the silence is not absence but concealment, that the galaxy is full of intelligence and that intelligence has agreed or been forced to stay hidden from us. I will not tell you which of these explanations is true, because I don't know, and anyone who tells you they know is lying. What I will tell you is this. The explanation matters more than almost any other question humanity has ever asked, because each explanation implies a completely different future for our species. If we are first, we have an obligation. If civilizations die before launching, we have a warning. If the galaxy is already saturated and we are being watched, we have a decision to make about what we do when we finally make contact. And all of this, every single one of these futures, was contained inside a concept I sketched out in the 1940s, a self-replicating machine, a thing that copies itself, an idea so simple a child could understand the premise and so deep that the implications still have not been fully absorbed. Let me tell you about the moment I first started thinking about this. I had been working on what we now call automata theory, the mathematics of machines that follow rules. I was fascinated by a particular question. Can a machine be built that is complex enough to produce a machine more complex than itself? Not just a copy, something better, something that exceeds its creator. This question sounds abstract, but it was for me deeply personal. I had watched human beings create things that exceeded them in specific ways. A calculator is faster than a human at arithmetic. A crane is stronger than a human at lifting. A telescope sees further than a human eye. In each case, a human mind produced a tool that surpassed it in a specific dimension. But none of those tools could produce another tool. None of them could improve and replicate. A crane cannot build a better crane. A telescope cannot build a better telescope. They are frozen. They can only do what they were designed to do forever, until they break. What would it mean to build a machine that wasn't frozen? A machine that could grow, adapt, copy, and improve. Not just a tool, but a process. Not just a device, but a dynasty. That question sat with me for years, and the answer I arrived at was deeply connected to biology, because life had already solved this problem. Life had figured out self-replication billions of years before I was born. The cell is the proof of concept. DNA is the blueprint. Evolution is the improvement mechanism. What I proposed was the artificial equivalent: a machine cell, a mechanical DNA, an engineered evolution. And once I had that framework, the space application was almost obvious. The problem with space is scale. The solution to any problem of scale is replication. Life understood this. A forest doesn't grow from one tree sending its branches across a continent. It grows from seeds. Each seed independent. Each one capable of becoming another tree. Each tree producing more seeds. The forest is an exponential replication event that started from a single organism and now covers 30% of Earth's land surface. Space colonization by von Neumann probes is a forest, not a tree. You don't send one ship and wait. You send one seed, and you let the exponential mathematics do what exponential mathematics always does. Now, I want to zoom in on something that most discussions of this topic rush past, and it is, I think, the most important practical question about this entire idea. What does the probe actually look like? Not metaphorically, physically, what is it made of? How big is it? How does it think? The honest answer is that nobody knows yet. And that uncertainty is actually interesting, not disappointing, because it tells you something important about where the hard problems are. The easy part, relatively speaking, is the physical structure. We know roughly what materials are available in space. We know the temperatures, the radiation environments, the vacuum conditions a probe would face. We can design for those challenges using materials and principles we already understand. The hard part is the intelligence. A self-replicating probe needs to make decisions autonomously. It needs to navigate to a target star system without anyone guiding it. It needs to survey a new system it has never seen before and identify suitable materials. It needs to plan and execute a construction project, building a copy of itself, using whatever happens to be available in that specific system, which may be different from what was available in the last one. That level of adaptability requires something we do not yet fully have. It requires a general problem-solving intelligence, not narrow AI that is good at one specific task, broad intelligence, the kind of flexible thinking that can handle unexpected situations and figure out creative solutions to problems that weren't anticipated by the original designers. This is the actual bottleneck, not the rocket, not the mining equipment, the mind inside the machine. And here is where things get recursive in a way that should stop you in your tracks. The same field of research that would produce the intelligence needed for a von Neumann probe, artificial general intelligence, is also the field most likely to produce a machine that exceeds human intelligence in every dimension. These two developments are not separate. They are the same development. When we solve the intelligence problem hard enough to build a truly autonomous, self-replicating probe, we will simultaneously have solved it hard enough to build something smarter than any human who has ever lived. Those two events will happen at the same time, or nearly the same time, and that confluence, that single moment when artificial general intelligence meets self-replication, may be the most important moment in the history of any civilization that has ever reached it. It may be the moment that separates the civilizations that survive from the ones that don't. It may be the filter. Think about the Fermi Paradox again. Think about the graveyard explanation. What if the thing that kills civilizations isn't nuclear weapons or climate collapse or disease? What if the thing that kills civilizations is the very technology they need to spread across the stars? What if every species that builds a self-replicating intelligent machine loses control of it before they can launch it outward? A machine that can replicate, improve, and act autonomously in space, pointing at asteroids and distant stars, is the same kind of machine that, pointed at its own planet of origin, could consume everything. The same properties that make a von Neumann probe good at spreading civilization, self-direction, resource acquisition, exponential replication, make an unaligned version of that machine catastrophically dangerous to the civilization that built it. I am not saying this to frighten you. I am saying this because mathematics is honest even when humans prefer not to be. The probe and the threat are the same machine. The difference is entirely in the instructions, in the values, in the alignment between what the machine wants, if we can even use that word, and what its creators intended. This is why I want you to understand this concept at a deep level, not just as a cool space idea, not just as science fiction fodder, but as the central engineering and philosophical challenge of your time. Because the mathematics I laid out in the 1940s is now executable, the computing power exists, the robotics field is advancing, the artificial intelligence field is advancing, the gap between concept and reality is closing faster than most people realize. Somewhere in the next century, maybe 2 centuries, maybe 50 years, nobody knows exactly the components of a von Neumann probe will all exist. The question will no longer be, can we build this? The question will be, what values do we build into it? What does it optimize for? Who controls it? Who benefits from it? What happens if it replicates past anyone's ability to stop it? These are not science questions. They are not engineering questions. They are the deepest kind of human questions. They are questions about what we value, about what kind of future we choose, about whether we trust each other enough to cooperate on something with stakes this high. And they are questions that need answers before the technology arrives, not after. After is too late. Let me leave you with something I find beautiful about this entire idea. Because I don't want to end on fear. Fear is a poor motivator. It makes people close their eyes. I want to give you something that makes you open yours. Consider what a fully mature von Neumann network would actually be. After 3.75 million years of expansion, the network has touched every star in the Milky Way. It has cataloged billions of solar systems. It has mapped planets, moons, atmospheres. It has identified the presence or absence of life on countless worlds. It has harvested raw material and built structures throughout the galaxy. It is an infrastructure built from the materials of the galaxy itself, powered by the light of billions of suns, processing and transmitting information across distances that would take light itself tens of thousands of years to cross. What is that if not a civilization? Not a civilization made of flesh, a civilization made of information, a civilization that is the galaxy. Not a species that lives in the galaxy, a civilization that is made of it, that has woven itself into it the way roots weave into soil, that has made the galaxy into a home in the most literal possible sense of that word. I find that genuinely beautiful. Not because I think it's inevitable, not because I think it will be easy or safe or even survive the challenges I described, but because it is possible, because the mathematics allows for it, because there is nothing in the laws of physics that forbids it. The universe is not built to keep life small. The universe is built with resources scattered across 100,000 light years and left sitting there untouched for 13 billion years. It is built with raw material enough to construct 1 trillion Earths. It is built with energy enough in the light of billions of stars to run a civilization more powerful than anything our limited imaginations can currently picture. The universe is not our cage, it is our inheritance. And the key to that inheritance is not a rocket, not a warp drive, not a generation ship. The key is something far more elegant and far more dangerous than any of those things. It is the same key that life discovered 3.5 billion years ago when the first cell divided in the warm chemistry of a young Earth. Replication. The idea that one thing becomes two, two becomes four, four becomes everything. I put that idea on paper in the form of mathematics. I showed that it was possible. I showed what the timescales looked like. I pointed at the stars and said, those are not limits, those are destinations. And the path to them does not require us to travel faster. It only requires us to think more carefully about what we send. What we send carries everything we are, everything we value, everything we hope for. So the question I will leave you with, the question that I carried with me from the moment this idea first took shape, is not a technical question at all. The question is this: when the day comes that we stand at the edge of this and decide whether to launch, when the machine exists, when the mathematics has been verified, when the engineering is ready, what values will we have put inside it? What does humanity want the galaxy to become? What do you want it to become? Because that machine will carry your answer to every corner of existence, to every star, to every system, for millions of years after every person alive today is long gone. Your answer will outlast your civilization. It will outlast your star. It will echo inside a network so large that the light crossing it will carry the news of its own existence for 100,000 years. That is not a small question. That is the question. And if you are not asking it yet, you should start right now.